The topic is portable ops using simple, effective antennas. I'm also going off a little bit deeper. We need things like coax. Hopefully the DIY mentality exists and you might want to build your own. So my topics are off-center Fed Dipole, which is a favorite of our very own Ted Edwards. The basic dipole, I think we all have built one or certainly use them. The NVIS Halfwave, another easy to assemble, easy to deploy antenna. And then the NVIS type of deployment and coax, which is very important for your station. And then if you're into DIY, I'm going to touch briefly on transformer design. And then finally, things to have in your kit when you go out in the field. So, talking points, why that design is popular, practical characteristics of each of these antennas, strengths in field deployment. Some are easier to set up than others, but they're all basically very simple. Each one has some limitations, both in the setup and in its transmission characteristics. They exhibit pattern behaviors that can work against you or work for you. And a brief touch on calculating and building those antennas. So the very first one is the off-center Fed Dipole. There's a small example up here in the, there goes my cursor, in the upper right corner. And it's basically a multi-band HF wire antenna where the feed point is moved off-center. It's very popular because it'll cover multiple bands. There are no traps required. It's mechanically simple. It's a big favorite of Ted. And by the way, I asked Ted if he would let me use his name frequently in this presentation. I shall. It has good efficiency when it's deployed. The impedance at the feed point is typically between 200 and 300 ohms. And you do need a Balun, in this case a 4-to-1, to match the antenna to the coax. It exhibits noise levels very similar to a dipole. And some of the strengths of this antenna, they're very easy to deploy between trees or a suitable telescopic mast. And I'll bring up telescopic mast more than once in this presentation, just so you know. Last night when I was rehearsing, I went on Amazon and guess what? A 30-foot painter's pole, telescopic, for $60. So these things are readily available if you want to add a mast to your antenna collection. This antenna does not require any radials, and combined with a tuner, you then have multi-band capabilities. And if you mount this in a low position, such as NVIS, you're going to have very good regional performance. Mounting it higher, say in your home QTH, DX performance can occur. So basically an all-around good antenna. It does require a high-quality Balun. Common mode current is a problem with this design, so a quality choke Balun is strongly suggested. The pattern's going to vary significantly by band, and you may find your SWR also varies. Depending on the frequency, the orientation, and the height of the antenna above ground, it's going to change the radiation pattern. These antennas are typically not directional, but you may have multiple lobes that can favor certain directions. You can purchase or build these. The building of them is pretty basic. Take 468, divide it by the frequency in megahertz. This will give you the total length in feet. Add several percent so you've got some room for trimming, and you're good to go. The typical offset feed point is a third of it on one end and 2/3 on the other. However, Some people have experimented, found that 30%, 70%, or 36 and 64%. So enjoy if you decide to build one. And now the basic antenna. You can see the dipole example in the upper corner. This is a great single frequency antenna. When I first was licensed as a teenager, the very first antenna I built was an 80-meter dipole. I used a bow and arrow to put lines up in 2 trees in our yard, and this antenna, being oriented north and south, gave me really excellent communications across the United States. So I recommend them. Simple. Using 3D printing, you can make your own insulators and center feed points. They also can be deployed as an inverted V, which only needs one support. And the best performance tends to occur when the antenna is 3/10 to 5/10 of a wavelength above ground. However, they will work at whatever you're able to put them up. Paul was nice enough to bring a fan dipole, which we've strung across the back of the room here. And that particular antenna consists of several wires cut for different frequencies. This particular one, Paul said, is effective from 40 meters to 10 meters. So one antenna, one dipole, you're in business. Same calculations, 468 divided by the frequency, add several percent to that dimension so you have something to trim. Then the end-fed half-wave, which I think is one of the favorites because typically you only need one support. They're lightweight, no traps, they have multi-band capability. They're naturally resonant on its fundamental frequency. However, if you cut it properly, and there are tables out on the internet to let you know, it will resonate on other frequencies. One of its pluses or minuses, depending on how you look at it, has a very high feed point impedance, somewhere around 2,000 to 3,000 ohms. But ease of deployment, no radials needed, and efficient use of power. However, this antenna is susceptible to common mode current and does need a choke. I've read they need a counterpoise, they don't need a counterpoise. So there are differing views depending on who you speak to. The feed point Unun needs to be of a high quality due to the high feed point voltage. This will also impact efficiency. As with any half-wave antenna, the radiation pattern will be affected by the height above ground, what frequency you're operating on, and the orientation of the antenna. It is not inherently directional. And once again, if you want to build it, we're dealing with the same formula, 468 divided by the frequency in megahertz. As I mentioned a moment ago, feed point between 2,000 and 4,000 ohms. So a lot of people have worked these antennas using different ratios on their Unun, 36 to 1, 64 to 1. Typically 49 to 1 is a good starting point. An additional high quality capacitor of 100 picofarads will compensate for the leakage voltage of the primary, which will improve the high frequency response of the transformer. And I do, in a moment, will show you that. The counterpoise is typically 5% of the longest wavelength you plan on transmitting. So 40 meters, approximately 2 meters in length for your counterpoise, and then a 1-to-1 choke following that Unun will help with common mode. And basically the matching transformer is the most crucial aspect of this antenna. And now we come into the near vertical incident skywave, NVIS. And NVIS can be any of the 3 antennas I've talked about. It's basically how that antenna is deployed. The beauty of NVIS is you find yourself using the lower frequencies, such as 10 megahertz range, which are applicable for much of what we would need it for. And they also give you regional coverage somewhere in the 60 to 300 miles. And another cool factor is they have a very steep near vertical angle of incidence when they're transmitting, and the F2 layer contributes to that. You do not need a great powerful transmitter. Your typical 100 watt works quite well. Going back to the vertical angles, living in Middle Tennessee, we have hills and valleys, so your repeater, your VHF, UHF may not work as well, but an NVIS station has a much better chance of communicating. So for best results, all the stations should be optimized, and the reason being, with NVIS, you have an issue of ground wave. If the stations are close enough, the sky wave and the ground wave will mix with the receiver at the receiving station side and cause multipath distortion, making your signal hard to understand. So lowering the antennas will help reduce the ground wave. And typically, you find 1/8 to 1/10 wavelength as a good starting point to position your dipole, your off-center fed, or your in-fed. Some people find that 1/20 wavelength results in the noise level being reduced. Additionally, a parasitic wire reflector that is placed on the ground underneath the transmitting antenna that's a bit longer than your antenna will narrow the SWR bandwidth somewhat and may result in some transmitter gain. This was this was something I ran across that someone had tested. If you suspend a dipole and you let it sag in the middle, so your feed point is lower than the two ends, you may gain between 1 and 2 dB of transmitted and reception. So another good choice would be the inverted V, and this works best if the apex angle is about 120 degrees or greater. So, and this goes back to Ted. He intrigued me enough with some of his presentations to research some of the antenna modeling software. This particular program is called mManagal. And so I have taken a 40-meter antenna. In this case of the dipole, it's the blue line you see right here on the y-axis. And I have modeled it at 10 meters above the ground. And as you can see, I have some vertical radiation, but wow, it really works perpendicular with a nice takeoff angle. So works really well for DX. And then taking that same dipole, but bringing the antenna down to 6 feet or 2 meters off the ground, you notice I have excellent vertical radiation in both directions, horizontal equally well. So this would give you an opportunity in that valley to get a signal out. And then the in-fed half-wave I discovered has some very interesting characteristics. Here's the antenna, the blue line going up in a diagonal. It is 10 meters supported on one end, and I've modeled it with 1 meter at ground level. And so I ended up with these very interesting patterns. So in looking at the horizontal, there is somewhat directivity towards the support of that antenna, but it will vary with frequency. And then the off-center fed dipole, really nice. So this one also is on 40 meters, about 10 meters off the ground, and you can see the vertical radiation running right along the wire, and then the perpendicular radiation, we actually have 4 lobes on the horizontal. So another good choice. Then you've built or you've bought one of these antennas. You need to be able to connect it to your radio. And something I discovered is quality coax makes a difference. I pulled this example out of my junk box, stripped it back, and I discovered I might have 50% braid coverage. This represents a loss. Who knows what else is going on? So good coax is really the most important part of your station after the antenna. And so you're going to find that it gives you superior signal integrity, long-term durability, consistent performance. It's going to maintain a precise impedance, probably going to be more reliable. They're using quality components, and it's going to reduce EMI. And certainly during field day, we have multiple stations going. So quality coax would be my first choice in that scenario. As you can see on the cheap coax, you're going to have a higher resistive loss. You're going to lose some of your signal to heat. There's probably going to be a dielectric loss because some of the plastics used are not of high quality. And then the construction quality will increase the AC resistance and potentially attenuate your signal. HF, not such a big deal, but certainly in the VHF and UHF frequencies. So some choices. I think we're all familiar with DX Engineering, ABR Industries, Davis RF. My favorite that I buy from is Messi and Poloni, which is an Italian company. They will ship it direct. Gigaparts here in the United States offers that product, but they don't offer all the cables or all the connectors. Some of the coax brands that I have used over the years, Andrew, Times Microwave, the Messi and Poloni, CommScope, any of those are well-known companies that make a very good, reliable product. So now, touching briefly on building your own antenna with either a Balun or an Unun, or perhaps even both. So here's what we find out. A Balun is an electrical device that interfaces transmission lines where two conductors carry equal currents in opposite phases, such as twin lead or dipole antennas. With unbalanced lines, where one conductor is ground and the other is coaxial cable, its primary functions are to convert signal types, match impedance, and suppress common mode currents. And then you encounter the Unun. There we go. This is basically a transformer that converts from unbalanced to unbalanced. And you're trying to match impedance between two unbalanced systems, such as your antenna and your unbalanced coaxial line. Its primary function is to minimize signal reflections and maximize power transforming by transferring the antenna's impedance to match the transmission line's characteristic impedance. So, in the spirit of DIY, I have built several transformers, mainly for the NFED, and some of the hams in the world have discovered that the efficiency of this particular ferrite, and I have examples of those here. This one is suitable for 200 watt SSB, 150 watt CW code. I'm using 16 gauge wire, and it's wound in what's called the auto transformer method, which basically consists of 16 turns. And then you can see the primary here. You connect this side to the ground. You connect the tap, which is at 2 turns, to the center of your coax. And then your antenna, of course, is connected here at the end. These perform really, really well. And you can measure the efficiency if you so desire. If you have a nano VNA, you build 2. You can see my 100 picofarad capacitors. And if you need to have an efficient transmission, I would recommend these. Other people can confirm it. There's a ham in the UK, Colin, MM0OPX, who several years ago built a portable hex beam. Well, I built one myself and brought it to field day 2 years ago and deployed it. So he does a lot of antenna work, and here's what he discovered using the same method, using this core with a quality 100 picofarad capacitor. He's come up with efficiencies, as you can see, all in the 90% range or very close. Now, anybody that happens to own the typical FT140 or the FT240 toroids, they're not that much less efficient than this. This is just an option. I like it because it's so small. And I'm going to put it out here that I have some of these. If anybody here wants to build a QRP version, this is 22 gauge wire. I'm gladly going to give out one of the toroids. These are all 43 mix, so very comparable to the FT240 and the 140s. The current Balun, which we need for our off-center Fed Dipole, force equal and opposite currents in balanced lines, while voltage balance force equal and opposite voltage at the output terminals. And so the current Balun presents a high impedance to common mode currents while allowing differential mode currents to pass with minimal loss. These are generally superior in suppressing common mode interference because they maintain balance even when the antenna legs are asymmetric or the load is unbalanced. These work really well with our dipoles since typically you don't have perfect symmetry. And then voltage balance transform, Voltage balance use transformer action to step impedance and ensure equal voltage at the balanced ports. They rely on particularly symmetrical load to maintain current balance. If the antenna is unbalanced, the voltage Balun may fail to suppress common mode currents. Going back to earlier, adding a common mode choke in line is probably a good habit to get into. They're used for specific impedance matching or when galvanic isolation is required. So, talking about the 4-to-1 for the off-center Fed current balance, you must use 2 separate toroids, and these are actually 2 common mode chokes wired in parallel. And if you use a single core 4-to-1, which is typically called a Ruthroff voltage Balun, you may not be able to handle high power or low impedance as well as with dual core current Baluns. Stacking these can increase power handling or choking impedance. So the common ones, I think we're all familiar with, are the FT140s and the FT240s with the 43 mix. There are also 31 mixes, which may be useful. In summary, the current Balun is preferred for common mode suppression in real-world scenarios with imperfect antenna symmetry. And the voltage Baluns are transformer-based devices that force voltage balance but may allow common mode current if the load is uneven. So another UK ham, he has a rather interesting, easy to build design for a 4-to-1 current choke, and you wind 2 separate chokes on each of the cores using bisectional bifiller windings. The radio tuner end is wound in parallel and the antenna side is wound in series. You simply connect the short leg of the antenna to the black lead and the long end goes to the red lead. So here's an example of that. When I was testing it, I found that this configuration, and by the way, this is a 240-43 mix toroids. What you can't really see well, I didn't have any large resistors. That's an 1/8 watt, 192 ohm. Ideally, you want a 200 ohm resistor for testing, but at any rate, I connected this to my Nano VNA and discovered I was barely over 1-to-1 SWR. So very efficient. I'm using paired power cord just because it's easy to see what's positive, what's negative. In this example, I used some 31 toroids and went with 12 turns. You can see how I'm wired. You at the input in black to black, red to red, and then at the top we're connecting in series red to black, and then your antenna goes out on the short leg here, long leg here. Once again, this probably cost me under $10 for the wire and the toroids. And then combine that with some of the 3D printed center cores and add some wire of your choice, you've got a really nice off-center dipole for easily $20–25 range.
So this is a current Balun?
This is a current Balun.
And you're using a type 31, but you talked about 43 earlier.
Yes, you can use other mixes. What I learned in my research, the differences may occur how some mixes will favor the low end of the HF spectrum, and some mixes will let you use the whole spectrum. So it really depends on your application. And the 31s, and I may be quoting this wrong, seem to favor the low end. So, moving on, you can stack them. Some of the testing shows very little interaction between cores, so this allows you to put it in a much smaller utility box. So, coming to things I think might be useful when you're out in the field. You've already got your antenna and you've got your radio. I think some additional tools, a VOM would be great to have in your kit, some test leads, additional antenna stakes, some nylon or Dacron rope, antenna insulators, backup power source, whether it's more batteries, a generator, an AC supply, you just never know. And then a spare antenna. What if yours is damaged during a storm because you're deployed and you lose that one? So having a backup, not a bad idea. This one to me makes the most sense. A spare microphone if you're SSB, or a spare key. Take away either one of those items, your radio is off the air. Extra coax with connectors, flashlight, paper and pencils. If that laptop or tablet fail, old school may be the best approach. Electrical tape, duct tape, stranded wire, various cables to connect your radio, your tuner, etc. And then this one I think is most important because I have found myself months later going, how do I use that feature on the radio? So throw the owner's manual in your kit. Then it struck me as, okay, we've dealt with the radio, we've dealt with the antennas, we got to take care of the human. So suggestions, favorite snacks, water, medicines you might take, aspirin, a first aid kit, rain gear, extra clothing depending on the time of the year, shoes and socks, nothing worse than wet feet, gloves, hat, sunscreen this time of year especially. Bug repellent is another one. You've also matches, a lighter, okay, you might need a fire. Hand wipes, I doubt if there's going to be a bathroom in every location. Identification documents, who you are, why you're there. For your phone, tablet, computer, another power source. Have cables for those devices. Personally, I prefer a headlamp because that leaves my hands free. Your mileage may vary. Toilet supplies, because once again, you don't know what you're into. So, as I mentioned earlier, anybody wants to build a POTA type in-fed antenna, I'll happily donate toroids for that. And questions, comments?